Okay, good morning. Last day of classes. How's it feel? Probably feels pretty good. Final exam time. Okay, so today we're just going to wrap up some trig material. We'll start kind of review by example, and then we'll head into some just an extension of what we've been doing, so just so that we have a little bit more coverage, and then you're all good. I think Shaun has posted a practice final exam for you guys, so that might be good to look through, but I think we're ready to go here. Okay, so we'll start kind of review by example, just to get into the swing of things. So for all these trig questions, what you'll find is having that unit circle handy that we were working with last day, this one. In fact, I'm going to steal it right away. And you can develop this right on your own using those special triangles if you want to, or I would probably just have this this unit circle handy somewhere. Okay. So if we are doing an example like where we left off last day, let's say find all angles. Oops, sorry, must be Monday. My writing is worse than usual. Find all angles for which cos theta is equal to 1/2. Okay. So remember, theta is an angle, or if you prefer, you can use t. So theta or t are kind of our typical angle names. Right. So theta or t, that's our angle, and the angle is the first thing that's kind of listed around this unit circle, right? And so it usually has a pi in there somewhere. If we're dealing in radians, if we're dealing in degrees, it would have a little degree circle, right? So it always has the unit if you're working in degrees. Okay, so we want to know, find all the angles for which cos theta is equal to 1/2. Now, cos theta, remember last day, we said that the cosine of the angle is really the x coordinate in the terminal point. Okay. So sine theta then is the y coordinate, right? So if we look at all these terminal points, we've got x, y coordinates, which is really, so here, this pi over 6, right? That's our angle. So the cosine of pi over 6 must be root 3 over 2, and the sine of pi over 6 must be 1/2, right? And then we can work our way through the circle here. And as we move through these quadrants, notice here in the first quadrant, x's are positive, y's are positive, so both values are positive. And then we move into the second quadrant here, x is negative, y is positive, so all our x values must be negative and all our y values must be positive. And then we can work our way through the circle. So we want to know which angles give us a cosine of 1/2. Well, if we go through, cosine is our x value. So here's one value that gives us 1/2. I'm just going to scan the circle and just to see. So here's negative 1/2. That's not positive 1/2, so it doesn't satisfy the criteria that we have. Negative 1/2 again. No. We know that both of these two quadrants are going to give me a negative x value. So that's not going to work, right? But we check them either way, right? And then here, I get an x value of 1/2 again, right? And so what happens is I can go, let's see here, from pi over 3, right? But then I also have this 5 pi over 3, or if you prefer, right, it might be nice to talk about the negative angle because it's closer, right? And we established that, okay, well, 5 pi over 3 in terms of a negative angle, so moving clockwise, is going to be, so 5 pi over 3 is the same as negative pi over 3, right? I'm just moving the same distance from 1, 0 to pi over 3 as I am to 5 pi over 3, but in the negative direction, right? And so we've actually got 2 points that make this happen. Okay. So on the unit circle, we see there are 2 points. Oops. Two points with cosine theta equal to 1/2, right? The first one being theta equal to pi over 3, right? That's in the first quadrant. The second one is where theta is 5 pi over 3, or if you prefer, negative pi over 3, right, moving in the clockwise direction, right? Just for some symmetry, right, and getting used to using these negative angles, just because they're closer, so they're easier to kind of think about, right? 5 pi over 3, it takes me, I don't know about you guys, but it takes me a little while to figure out, okay, where is 5 pi over 3? Whereas negative pi over 3, I kind of see it quicker. Okay. So pi over 3 or negative pi over 3. Here's the thing though, right? The reason we say all the angles is because, okay, so from here I can go pi over 3, but then I can go 2 pi, full circle around, another 2 pi, full circle around, another 2 pi, full circle around, right? And same thing from this negative pi over 3, right? I can go 2 pi, one circle around and get back to the same point, and then 2 pi, another circle around. So we can cycle through this, the unit circle, right? So it's really going to be pi over 3 or negative pi over 3, and then plus multiples of 2 pi. Okay. We can always add a multiple of 2 pi to get back to the initial terminal point, or to the same terminal point, let's say. To the same terminal point. Okay. So what we do is, therefore, theta can be pi over 3 plus 2k pi for k in the set of integers, right? 0, 1, 2, 3, 4, 5, 6, 7, blah, 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 to infinity, technically, right? Circle, circle, circle around. And theta is negative pi over 3 plus 2k pi. Again, k is in the set of integers. Okay. So that's where we got to last day, right? And whenever it asks you for all the angles, right, here, find all angles. I'll just highlight that maybe. Find all angles for which the cosine of theta is 1/2. So first thing you're going to do is you're going to scan the circle, find all the points where the x value is 1/2. And then remember, you can always add multiples of 2 pi, right? And usually we write 2k pi, but can write K2 pi, I guess. That seems weird. Okay. So that's the end of our review. Right? So now we're going to extend this idea to a couple of more trig functions. So this is section 5.2, and we'll call it trigonometric functions. Real numbers. Not very descriptive, right? We were already talking about trig functions, sine and cosine, right? But now we're going to extend it a little bit further. So we have already discussed sine and cosine, right? So now we're going to extend that to some other trig functions. So now we will extend those ideas to the other trig functions. And there are some other ones, but these are kind of our mainstays. So to the other trigonometric functions, or trigonometric functions. And I don't know if you remember, but I posted that handout. I said it was for December 2nd, but we're actually going to keep using it because I made it for December 2nd, but here we are. Okay, so first things first, here, right, we've talked about sine and cosine, but we also have tangent, which might sound familiar. We also have these cosecant, secant, and cotangent. We're going to call those the reciprocals. Okay, so here the reciprocal identities are down here. And in fact, I think that this box is a little bit easier to read, right? This first one is a little bit more helpful if you're dealing with triangles, right? So sine theta, SOHCAHTOA is the first line here. And then, of course, the cosecant, secant, and cotangent are just the reciprocals of the ones above it. But I actually don't find that this is that helpful unless you have a triangle that you're working with. Then, of course, we can always wedge a special triangle into and to use that for our angle, but I prefer to just use the unit circle that we have, right? That nice full one. But I am going to bring this inside here. Okay. So we've already talked about the sine and the cosine of an angle. And so the cosecant, okay, this here, let's say here, CSC is the cosecant, right? Sometimes it's hard to know how to say these things. CSC is cosecant, SEC is the secant, and COT is the cotangent. And of course, the tan is just, oops, I forgot the co on the cotangent. I jumped ahead in my mind, is just the tangent. Okay. So remembering that the cosine of, if we use t for our angle, right? So t is our angle. And so the cos of t is the x, and the sine of t is the y in the terminal point. So just remember that, okay? Then as long as you have this table to refer to, then we can easily find things like the cosecant of t. Well, that's just 1 over sine t. So you just take 1 over the y value in the terminal point of t, right? Secant of t, 1 over the cosine, so 1 over the x value in the terminal point of t. Cotangent, 1 over tangent, not that helpful if you don't know what tangent is. So you kind of want to go here first. So sine t over cos t. So the tangent is the sine, so the y value over the x value. And then, of course, if we take 1 over the tangent, you can rewrite the cotangent as cosine over sine. So it's just the reciprocal, right, of the tangent. Right. So here, the cotangent, notice that those are the same. So you only need one of those. I would probably opt for this one, right? But it depends on what you're working on. If you have the tangent, then it's easier to use this one. So that's why they're both here. But
quick question.
If you have the sorry, say that again.
Quick question. I'm just trying to make sense of my own calculator. So the cotangent and so on, would they also potentially be displayed as like tan to the negative 1?
No.
Oh.
That's the hard part. So those are the inverse functions, okay? But to do cosecant, secant, and cotangent on your calculator, you need these reciprocal identities. So that's really good. So let's write that down.
Okay.
Okay. In order to find cosecant, secant, and cotangent on, oops, I say and, but I wrote, no, I meant on, but I wrote and, I don't know. On your calculator, you will need to use the reciprocal identities. Right, which is this, I'll just bring that in here. Oh, of course, won't let me remove this, right? But those are the reciprocal identities. So if you need to find the cosecant of t, then you actually have to find 1 over sine t, or it's easier to find sine t and then just take 1 over that. So, so don't be confused, right? Don't use sine to the negative 1 because it's not going to give you the same value. That's the inverse sine, which we're not going to have time to get to. But if you go into Calc 1, then it'll be covered there. So don't worry. But we won't get into inverse sine or inverse trig functions this term because it's our last class. What are we supposed to do? So, so these are the ones that you'd have to use on your calculator to find these. Okay, but you should have a tan button, you should have a sine button, you should have a cosine button. So you can kind of knit them together. Okay. Let's do an example. Find the value of the following. Find the value of the following. A, the tangent of negative 3 pi over 4. B, the secant of 14 pi over 6, and C, the cotangent of negative 9 pi over 4. Okay. So what I want to do is I want to do the tangent one together, and then I'll give you a little bit of time to work through those second, the secant and the cotangent. And then, of course, we'll go through it together. The tan of negative 3 pi over 4, okay. Let's have a look at what is the tangent, right? So we know it's some sort of mashup of sine and cosine, just which one, right? And so I'm going to use this one, the sine of t and the cosine of t. So what I'm going to do is I'm going to rewrite the tan of whatever angle it was that I was given, I don't remember, and then rewrite it with sine of that angle over the cosine of that angle. Because I know how to find the sine and cosine. I don't really know how to find tan any other way. And this is the best way. So this is the same as the sine of negative 3 pi over 4 over the cosine of negative 3 pi over 4. Okay. Notice that I'm using this angle, I'm using it twice, once in sine and once in cosine. But of course, because it's the same, it's one angle, right? I'm just using the y coordinate and over the x coordinate of that terminal point. So here, we need to find the terminal point for negative 3 pi over 4. Okay, negative just tells me I'm moving clockwise in the clockwise direction. And let me, oh, it's been a while here. Let me bring this, this unit circle down so we don't have to scroll so much. Paste. Okay, so negative 3 pi over 4. So pi over 4, those are the quarter wave marks. So here, negative pi over 4, negative 2 pi over 4, negative 3 pi over 4 is the same as 5 pi over 4. Okay, so what I'm going to do is I'm going to say, okay, here's negative pi over 4. Oh, does that thing where it tries to anticipate what I want my shape to be. Sometimes it's useful, sometimes it's not. Negative 3 pi over 4 is at this point here. So the terminal point for negative 3 pi over 4 is negative root 2 over 2 and negative root 2 over 2. So I'll just indicate it like this: negative root 2 over 2, negative root 2 over 2. Okay. So this, right, this is the cosine of negative 3 pi over 4, and this is the sine of negative 3 pi over 4. Okay. So now I can just plug in those values, right? Sine of negative 3 pi over 4, I'm going to replace it with negative root 2 over 2, and same thing with the cosine of negative 3 pi over 4. I'm going to replace it with negative root 2 over 2. So then I get the sine of negative 3 pi over 4 over the cosine of negative 3 pi over 4 is the negative root 2 over 2 divided by the negative root 2 over 2. Okay. This is just going to cancel out, right? You can treat this, well, if you want to be proper, right? You've got a fraction over a fraction. So to simplify a fraction over a fraction, you have to flip the denominator and multiply, right? And so what you get is, if you cancel these negatives, because you know they're going to go away anyways, Negative over negative is a positive. So then you have root 2 over 2 times 2 over root 2, or you can just recognize that a over a is just 1, right? Anything over itself is just 1. But here it is. 2 cancel, root 2 cancel. So all I'm left with is that it's equal to 1. Yeah. So we can use the sine and cosine to develop all those other trig functions. Let's do the secant of 14 pi over 6. And then I'll let you do the cotangent on your own. How about? Give you a little bit of time. But this stuff is kind of hard, so I want to help you out. The secant of 14 pi over 6. Okay. So the secant, okay, let's go back to these identities here. The secant is the same as 1 over the cosine. So now I only need the x value at this angle, right? And so that's nice. So the secant of 1 over cos t, so I'm going to rewrite this. This is the same as 1 over the cosine of 14 pi over 6. This I know how to find, right? So the cosine is the x value. 14 pi over 6, I can simplify a little bit, right? I'll steal this, copy, paste. And I wonder if I can, now I can erase. I don't know, it's different paste modes, I guess. All right, so 14 pi over 6. So now I want to simplify it a little bit, right? I want to peel the onion, and so I want to take away any multiples of 2 pi. When I'm working over 6, right, 2 pi is 12 pi over 6. So what I'm going to do is I'm going to kind of shave it down so I don't have any loops around the circle anymore. So here I'm going to make a note that 14 pi over 6 is the same as 12 pi over 6, right? So you just need to look at what's the denominator and how do I get 2 pi out of that, right? 2 times 6 is 12, so 12 pi over 6 makes 2 pi plus 2 pi over 6. So here, this one is just one loop around, right? So here I'm starting and I did a loop around, and now I'm going 2 pi over 6. 2 pi over 6 is the same as pi over 3, right? Because pi over 6 and then plus 2 pi over 6. So here, pi over 3 is 2 pi over 6, which you would get if you canceled it too. So here, right, terminal point at pi over 3, which is 1/2 root 3 over 2. Okay. So 14 pi over 6, we chiseled it down until we had just pi over 3, fine. And we have this terminal point. So now I can rewrite 1 over the cosine of essentially pi over 3, right? 14 pi over 6, we chiseled it down to pi over 3. So the cosine is 1/2. So now I've got 1 over 1/2. So this becomes 1 divided by 1/2. Basically a fraction over a fraction again, right? 1 over 1 over 1/2, flip and multiply. And so I get 2. Okay. C, the cotangent of negative 9 pi over 4. I'm going to pause this for just 2 minutes, give you a. So even if you're not quite finished, because it's a little bit of a trickier one. It's the last one, right? So kind of sent you out on your own. So let's do this one. So we know, first of all, we know that the angle that we have to deal with is negative 9 pi over 4. Just remembering that the negative tells me that I'm moving clockwise instead of counterclockwise. But also we're dealing with the cotangent. So the cotangent is the reciprocal of tangent, right? So here the cotangent of t is 1 over tan t, okay? But we actually have two options. Right, we had the 1 over tan t, fine. Or if you prefer, the cotangent is also, you could go from here to here by replacing the tan t with sine t over cos t, and you would find that the cotangent of t is cos t over sine t. Right, so we've got two options. It doesn't actually matter which one you use, right? So we have note the cotangent of t is 1 over tan t, or the cotangent of t is cos t over sine t. Right? Doesn't actually matter which one you use. Because I'm going to find the terminal point, right, of negative 9 pi over 4, I think it's actually easier to use the second one, right, because it just uses the cosine and the sine, whereas here you would have to find the tangent, which is sine over cosine, and then take 1 over that. So it's that extra little step that we don't actually need to do. Right? I will use this one. Doesn't matter. So here, negative 9 pi over 4, let's think about, okay, well, 2 pi, that's a full revolution, right? So I'm going to kind of peel away multiples of 2 pi. And so 8 pi over 4 would be a full revolution. So here, yes, I'm moving clockwise, but it doesn't actually matter, but that's what I'm doing. So now I've gone negative 8 pi over 4. So now I just need to move another pi over 4, negative pi over 4 to get to negative 9 pi over 4. So let's focus on this little guy here. I need a different color, don't I? Let's do pink here. Negative 9 pi over 4 is the same as negative 8 pi over 4. Plus negative pi over 4. You can do minus pi over 4, but I just like to illustrate that together this makes negative 9 pi over 4, right? And as well as this angle being negative, right? So really what it says is that I'm just going to go to this point here, that's negative pi over 4. So I did a full revolution. In fact, I'll show it here. I did a full revolution this way, and then I did my negative pi over 4. So here's negative 8 pi over 4 plus negative pi over 4. Okay. So either way, we find the terminal point of negative pi over 4. Negative pi over 4 has terminal point root 2 over 2 and negative root 2 over 2. Root 2 over 2 and negative root 2 over 2. So now the cosine of negative pi over 4 or negative 9 pi over 4, doesn't matter, they end up at the same place, right, is going to be root 2 over 2, and the sine of that angle, whichever one you prefer, is negative root 2 over 2. Right. So here, what we can say is that the cotangent of negative 9 pi over 4, well, first of all, it's going to be the same thing as the cotangent of negative pi over 4. Right, so let's start there. And that's going to be the same as the cosine of negative pi over 4 divided by the sine of negative pi over 4. Okay. So here, right, the cosine of negative pi over 4 is root 2 over 2. And again, the sine of negative pi over 4 is negative root 2 over 2. So here we go. We just plug and chug now, right? The cosine of this thing is root 2 over 2 divided by the sine of this thing, which is going to be negative root 2 over 2. I've got a fraction over a fraction, so what I need to do is I need to flip and multiply the denominator. And this negative, because it's the only negative, I can just kind of float it outside. So it'll just hang out, and I know I'm going to have a negative number. So this becomes negative root 2 over 2 times 2 over root 2. Again, we get that same cancellation thing going on. The 2's cancel, the root 2's cancel, and so I'm left with negative 1. Womp womp. All that work just to end up in negative 1. So hopefully that's what you were able to get to. But I think the biggest kind of help is just to move around the unit circle and just peel away multiples of 2 pi in either direction, right? Whichever direction you're moving. So now we can kind of spice things up a little bit. We can say, okay, well, how about, what if I want to find all angles for which the secant of t is the negative of root 2. Okay. So now we have this all angles, right? So I'm going to find the first angle, right? And then I'm going to tack on multiples of 2 pi, right? Because I'm just going to cycle through this thing. And so find all angles for which the secant of t of some angle is negative root 2. Okay. And I'm just going to highlight again that once we find our main angle, let's call it, then we're going to tack on multiples of 2 pi. Okay. We know we can't deal with secant t on its own, right? But we can replace secant t with 1 over cos t. Okay, so let's just kind of start manipulating this thing until we see something that we can work with. So if 1 over cos t is negative root 2, okay, now thinking about 1 over cos t is a little bit hard, but I'm allowed to multiply this over to the right? And then what I can do is I can divide both sides by negative root 2. So I'm going to do it in 2 steps. You're welcome to do it in 1 step, but just make sure you keep everything nice and clean. So as 1 equals negative root 2 cos t. Okay. You can have brackets around the t if you want. Often we just drop them, and we understand that this doesn't say cos, that says cos t, so that sometimes it's useful to have the brackets. So now what I'm going to do is I'm going to divide this negative root 2 over. So I get 1 divided by negative root 2 is the cosine of t. Okay. This looks sort of familiar, right? especially if you're thinking about those special triangles, right? Then you have a side with a 1 and a root 2. I'm going to manipulate this a little bit because on my unit circle, I don't have a 1 over root 2 here, but I do have root 2 over 2, which I feel like I can manipulate to become 1 over root 2 or vice versa. So what I'm going to do is I'm going to float this negative up top because it's easier to spot it that way, and I'm allowed to do that. 1 over root 2, and then times root 2 over root 2. So I'm going to rationalize this thing. And this is what we did last day too, just to make that connection between 1 over root 2 and root 2 over 2. Multiplying fractions, right? I'm just allowed to multiply across. And so I have negative root 2 over 2. Root 2 times root 2 is just 2, is the cosine of t. Okay? So we need to find, on the unit circle, we need to find the x values, right? So all the angles that give a terminal point with an x value of negative root 2 over 2. Let's just summarize that here. We need to find all angles that give a terminal point with an x value, I should say x coordinate, an x coordinate of negative root 2 over 2. Okay. So again, right, I'm just bringing in this, oh, it clunked out. Let's see here, hopefully it'll stay with me. I wonder if I copied or not. Best to just copy it again. Copy. Hey, we lost that note I just wrote. I was feeling pretty proud for summarizing it too. Okay, I'll rewrite it, don't worry. You guys are like, oh, I wasn't worried. All right. We need to find, okay, what did I say? All the angles that have a terminal point. Now you probably have this written down already. A terminal point, oops, or a terminal point, that's what it was, with an x coordinate of negative root 2 over 2. Okay, so just kind of scanning this unit circle here, root 3 over 2. This one is root 2 over 2, but I want negative root 2 over 2. So just kind of get in the habit of, okay, if it's negative and it's on the x, well, my values or my angles have to be in quadrant 2 or quadrant 3. Right, so they can only be over here on the negative x-axis. So I'm going to scan here, and I notice that I actually have 3 pi over 4 gives me an x value of negative root 2 over 2, but also 5 pi over 4 gives me an x value of negative root 2 over 2. So I actually get two points. Right, so here, this one and this one. Okay. We find 2 angles that satisfy the criteria, because we just listed it above, that satisfy the criteria. So a t of 3 pi over 4 or I should say and, right? Because both of them satisfy the criteria. And 5 pi over 4. Because both of them are kind of over here, I'm not going to bother with making one negative, but it would be 3 pi over 4 and negative 3 pi over 4, right? But I'm just going to keep it 3 pi over 4 and 5 pi over 4. I don't really see a reason to kind of mess with it, but you can. Okay. So therefore, all angles include multiples of 2 pi. Multiples of 2 pi from these angles. So t must be 3 pi over 4 plus 2k pi, again, where k is in the set of integers, and t is in 5 pi over 4 plus 2k pi again, and again, where k is in the set of integers. Oh, that's a weird integer. In fact, both of them got a little sleazy there. Okay. What about, so that's, there's your answer. Let's do one that's a little bit weirder. So what if we find all angles, and again, I'm going to highlight that all angles for which, right, so we're going to do the same thing again, for which tan of t is equal to root 3. Okay. So earlier, right, we were given the secant, which we kind of morphed into something that we're able to pinpoint on the unit circle, right? Cosine and sine. So what I'm going to do is I'm going to do the same thing for tan, and I'm going to have to do a little bit of kind of molding to figure out which x and y values are going to give me root 3, right? Because they're going to be a fraction. So the tan of t is the sine of t over the cosine of t equals root 3. So I need it to be a positive value. What this tells me is that neither, well, both have to be positive or both have to be negative. To get a positive value, sine t and cos t must have the same sign. Right, but it can be positive or negative. Right? Negative over a negative makes a positive, and positive over a positive makes a positive. Okay, so where do I have values of the same sign? Well, here in quadrant 1, they're both positive, and here in quadrant 3, they're both negative, right? So here, I'm going to copy this guy in again, mostly because we need to be able to refer to it. Let's see here. So here, right, quadrant 1 and quadrant 3, right, Q1 and Q3. So that's where I'm going to focus my attention. Okay. That's where both of them have the same sign. And I need to find a terminal point with a y value over an x value that's going to cancel to root 3. Okay, so we need to find terminal points. It will be multiples, so that's why I'm making it plural, but I should leave it open for just having one, but there will be 2. So we need to find terminal points with x and y values that cancel to make root 3 when we take y over x. Okay. So of course, the only ones that are of interest, and I say of course because if I need a root 3, I'm not going to be able to pull out a root 3 when I only have root 2 over 2 to work with, right? So that one's out, right? I have root 3's in pi over 6 and pi over 3. So those are the ones that I'm going to focus my attention on. We can try, so here, let's just try it. Try a terminal point of pi over 6, which has root 3 over 2 and 1/2. Okay. Y over x, so here's my y and here's my x. Y over x is going to be 1/2 divided by root 3 over 2. Fraction over a fraction, right? I'm going to flip the denominator and multiply. And so I get 1/2 times 2 over root 3. Close but no cigar, right? These 2's are going to cancel, so I end up with 1 over root 3. That's not quite what I wanted, right? So then pi over 6 is not an option. Right? So this is 1 over root 3, which is not equal to root 3. Okay? So then we try pi over 3 instead. Okay? Pi over 3 at 1/2 root 3 over 2. We do the same thing. Y over x is root 3 over 2 over 1/2. Okay? Fraction over fraction, I flip and multiply. Hey, it's looking good already. Root 3 over 2 times 2 over 1. 2's cancel, and I'm just left with root 3 over 1, which is just root 3. So here, oh, I guess I should keep the same color. Looks like pi over 3 is the one I want, and also the combination that I want is x being 1/2 and y being root 3 over 2, or the negative versions, negative 1/2 and negative root 3 over 2. Okay, and so therefore, the angle we want, or an angle we want, is pi over 3. Okay. But then if we also look at, hey, where did I put it? So here, pi over 3, that's one of the ones that we want, right? This one. And I'm also allowing for the negative versions of these, right? So now I need to look at negative 1/2 over, and then negative root 3 over 2. So this is the other one that I want. So 4 pi over 3. What we're going to notice, or what you might notice, is that here, you can go through the origin, right? There's a distance of pi here. So tangent has that special property of we're going to cycle through terminal points, but not in multiples of 2 pi, just pi. So what we can do is we can kind of shortcut this, and we can say pi over 3, right? That's my main angle, let's call it. plus pi, right? That gets me to that other point. Plus pi gets me back to that point. Plus pi gets me back to that point. We say that tan has a period of pi instead of a period of 2 pi. We're not going to get into that because we don't have time. But that's what it's called. And so what we'll notice is that tan cycles in cycles of pi rather than 2 pi. Okay. The other angle we want is 4 pi over 3. In fact, because it's so far away, of course, you don't have to copy. Okay. So we notice, right? I'll say what we will find is that tan, so the tangent, cycles in multiples of pi, instead of 2 pi. We also say tan has a period of pi instead of a period of 2 pi. So what we do, right, is we don't actually need this 4 pi over 3 because now we just, instead of saying multiples of 2 pi, I'm just going to move in multiples of pi. So then what I'll say is that t must be pi over 3 plus pi, or k pi, rather. So therefore t is pi over 3 plus k pi, right, not 2k pi, where k is in the set of integers again. Okay. So sometimes we'll have functions that are a little bit more involved, and so we'll need what we call the fundamental identities. And we already have it in the handout, but I'll bring it back in. To solve some more complicated trig functions, we need to use some fundamental identities. And there are lots more identities, especially trig identities, but these are the ones that we kind of rely on a lot. Some fundamental identities. So where is that handout? There. Okay. So this is the same as that thing I just brought in earlier, right? But to save us some writing here, the ones I'm talking about specifically are these Pythagorean identities. So we've already talked about these reciprocal identities. So we use those a lot, right? If we have to find things like cosecant, secant, cotangent. And now we're going to expand to the squared values. So sine squared, cos squared. So sine squared is just sine t times sine t. So that can be hard to kind of wrap your head around, but sine squared is just sine t times sine t. Same thing with tan t. Tan squared t is sine squared t over cos squared t. Okay, so you can just replace these with the squares. You can move back and forth between these. We're not going to focus so much on that. what I want to do is just work on these. You can move back and forth between these if you divide by sine squared t or cos squared t. Either way, you're going to end up at one of these other identities. So, but don't worry. So let's see here. Where do we go? Yeah. So for example, suppose the cosine of t is -4/5. Already we notice that that's not one of our terminal points that we're used to seeing, right? But that's okay, we can handle it, and I'll show you how. So the cosine is -4/5, that's okay. And the tangent of t is less than 0. Okay. What does this tell me? So here, I know that the cosine is negative and the tangent is also negative. So cos is negative. So remembering that the tangent is sine over cosine, right? So sine t over cos t is also negative. In order for that to be able to happen, right, if cosine is already negative and I need it to stay negative overall, then sine t must be it must be positive. Ugh, confuse you. Last thing I do. No, sine t must be positive. So sine t over cos t is also negative. So sine t must be positive. Now I know which quadrant I have to be in, right? Sine t, that's my y value. So y is positive and x is negative. Right? So here in my xy plane, okay, so cosine, so x is negative, so I'm over here, and I've got a positive y, so I'm over here in Q3, or sorry, Q2. Must be in Q2. Okay. So that's something that we're going to hang on to. Okay. The cosine, so I know the cosine and I know which quadrant I'm in. And oh, I didn't write down the question. I just said, hey, suppose this is true. Fine. Find the value of sine x. Uh-oh. I'll continue I didn't finish my question. Oh my bad. Find the value of sine x. Or sine t rather, sorry. It says x, but I'm going to use t because I want to emphasize that it's an angle. So finding the value of sine t is going to be, okay, so I have the cosine. I know that my sine t must be positive. And what are some things that I could use, right? So here I see that cosine is in the secant, but that also means, okay, so then I've got 1 over cosine squared. Fine, I can do that. And then 1 plus 1, and then tan squared is sine squared over cos squared. So I could do something there, but it seems like a lot of work, right? And I could do something even worse here, but this is my easiest identity. So what I'm going to do, if I want to find a sine, right, I look for, and I have a cosine, I look for the identity that has the most of my players. Sine squared plus cos squared equals 1 should do the trick. Since sine squared t plus cos squared t is 1, okay, what I can do, cos squared t is just cos t squared. Okay. So here, cos squared t is the same as cos t squared. Okay, same thing with the sine squared t. Sine squared t is sine t squared. You know? It's pretty unusual that we're allowed to just play fast and loose with the squares, right? But in this case, we're allowed to. And so if I have the cosine, what I'm going to do is I'm going to plug it in, and then I'm going to try to solve for this sine. So I can rewrite this as sine t squared, if it helps, right? Just to visualize, plus, and then the cos t negative 4 over 5 squared is equal to 1. Okay. So what I'm going to do is I'm going to bring in this square. So I get sine t squared plus negative 4 squared is 16 over 25 is equal to 1. Okay. Solving for sine, I need to move the 16 over 25 over to the right-hand side by subtracting. And so I get sine t squared is 1 minus 16 over 25. Okay. In order to simplify this, I need to get a common denominator of 25. I usually just multiply by whatever I want my common denominator to be. So here, I'm just going to indicate that by 25 over 25. So 1 times 25 over 25. So sine t squared is 25 over 25 minus 16 over 25. 25 minus 16 is 9. 9 over 25 is sine t squared. All I have to do now is I have to take the square root. But just remember, when you take the square root, you actually get the positive and the negative versions. So we get sine t is the plus minus the root of 9 over 25. What's nice is this root is going to pull in over the 9 and the 25 and simplify to something nice. So sine t is the plus minus of 3 over 5. But, right, earlier we established that, and you could go back and figure out which one it has to be after the fact, but I just wanted to introduce, okay, so knowing that the tangent is less than 0, so meaning it's negative, I have to be in Q2, right? And so sine t must be positive. Okay. Since sine t must be positive, we know that sine t is 3 over 5. Awesome. Okay. We'll do one last example. Then you can breathe a sigh of relief. That'll be it.
Oh, don't worry, we still have finals.
Yeah, that's true. But after that, done with this course. So very similar. but now I'm going to use the secant. Okay, so suppose, and I'll write out the entire question this time so I don't miss a crucial part. Suppose the secant of x, or let's use t instead. The secant of t is 13 over 12. And the cosecant is greater than 0. What is the value of cosecant of t? What is the value of the tan of t? Okay. So what I'm going to do, right, is I have secant and I want tangent. So what I'm going to look for is some identity that ideally only uses these two values, right? Secant and tan in some sort of combination. If not, I might have to incorporate and use multiple identities to get to my final result. And then the cosecant of t being greater than 0, so being positive, is just meant to help me find out which quadrant I'm in. Okay, so I'm going to focus on secant and tan and try to find an identity that's going to work. So I go back to my identities. And here it is, staring me in the face. Tan squared t plus 1 is the secant squared of t. So that's the one I'm going to use because it has everything that I need. I can manipulate this one. Like I said, we can divide by sine squared or cos squared and kind of get to one of these two. But the easiest way to go about it is just to find the closest thing to what we want. So tan squared t plus 1 is the secant squared of t. We see that the tan squared t plus 1 is the secant squared of t. Yeah. So what I'm going to do, if I want to find tan t, I'm going to put in secant of 13 over 12 and then square it and try to solve for my tan. So I get, and just remember the tan of t squared is the same as tan squared t. Plus 1 is, and it was 13 over 12 squared. Okay. I'll have to use my calculator because otherwise I'll mess this up for sure. 13 squared is 169, right? Because it's just a fraction in here, I'm allowed to bring this power inside as long as I bring it onto the numerator and the denominator. So 169 over 12 squared is 144. 169 divided by 144, I'm just going to see, it doesn't seem to simplify any further. That's okay. So tan t squared plus 1 is this. So now I'm going to subtract 1. And in the process, I know I'm going to need a common denominator of 144. So I'm actually going to multiply this by and turn this 1 into 144 over 144. Okay. So here, maybe over here, 144 over 144. Before I subtract it over, just to kind of get in the groove here. So tan t squared is 169 over 144. Oops. Minus 144 over 144. 169 minus 144 is 25. Hey, that's a nice number. I anticipate having to take a square root here. So tan t squared must be 25 over 144. And so if I take the square root, I get tan of t is the plus minus root of 25 over 144. So this is going to be, because I've just got a fraction in here, I'm allowed to bring this root inside on both the numerator and denominator. So I get plus minus 5 over 12. I need to decide whether my whether tan is going to be positive or negative, right? So in the previous question, we did it first, and now I'm going to leave it till the end. But in the end, we're going to use the fact that the cosecant of t is greater than 0. So here, we need to decide if tan t is positive or negative. Okay. So the cosecant, cosecant of t is greater than 0, and the cosecant of t, remember, was, just want to grab it here, is 1 over the sine of t is greater than 0. Okay. So in order for that to happen, sine t must be positive. Okay. And let's see, what else, what other clues? Oh, secant t is also positive. And we know, and secant t is also positive. And secant, where's secant? Is 1 over cosine. So therefore, sine t and cos t must be positive. So tan t, which is the sine t over cos t, must be positive. Therefore, tan t is the positive version 5 over 12. And a little bit over time. My apologies. But, oops. That concludes the course. You did it. I'll see if I can find a fun sticker. All right. Any questions?
None that I can't discover on the final.
Sounds good. Oh, well, thanks so much, you guys. It's been my pleasure. And good luck on your final exam.
Thank you. I'll be seeing you next semester.
Awesome.